Welcome! Today, we're diving into a really cool scientific principle that literally lets us measure the invisible. We're talking about a law that can look at a perfectly clear drop of liquid and tell us exactly what's hiding inside, all by using the power of light.
So think about it for a second. How would you actually do that? You've got a solution, and you need to know precisely how much of something, say DNA, is in there. You can't see it, you can't just put it on a scale, so what do?
Well, the answer lies in a machine like this one, a spectral photometer. This amazing device uses light to measure the concentration of a substance even in a teeny tiny drop. It's a total cornerstone of the modern lab, but you might be surprised to learn that the idea behind it is actually really old.
That's right. The technology we're looking at is totally cutting edge, but it's all built on a scientific law whose story started almost 3 centuries ago.
It was kind of like a scientific relay race across hundreds of years. It all kicked off in 1729 when Pierre Bouguer noticed that light gets weaker as it passes through something. Then in 1760, Johann Heinrich Lambert came along and put some math to it, connecting that light loss to how thick the material is. But it was August Beer in 1852 who added the final game-changing piece. He connected it all to the concentration of the stuff in the material.
And that's how we got the Beer-Lambert law. All it really says is this: the more stuff you have dissolved in a solution, the more light it's going to soak up. It's a simple, direct, and incredibly predictable relationship.
And that beautiful simplicity is captured in an equally elegant equation. Don't worry, you don't need to be a math whiz for this one. This is the key that unlocks the whole thing.
There it is. A equals epsilon BC. This one little formula is the mathematical heart of the Beer-Lambert law. It's the engine humming away inside every single one of those spectral photometers.
So let's break this down real quick. A is for absorbance, that's the thing the machine actually measures. Epsilon is the molar absorptivity, which sounds complicated, but it's just a unique number for any given molecule. Think of it like a chemical fingerprint. That's how the machine knows it's looking at DNA and not protein. They have different fingerprints. B is the path length, which is just the distance the light has to travel through the sample, and the machine keeps that distance fixed. And C, well, C is for concentration. That's the prize. That's what we want to know. So if the machine measures A and we already know the epsilon fingerprint and the fixed B distance, solving for C is just simple algebra.
You know, an easy way to think about it is like sunglasses. The darker the tint, which is basically a higher concentration of dye in the plastic, the less light gets through to your eyes. The Beer-Lambert law just puts a really precise number on that exact effect.
Okay, so that's the theory. But how does a modern instrument actually take that 300-year-old law and use it to turn a drop of liquid into solid data? Let's take a look.
It's a surprisingly straightforward process, really. First, a light source, usually a xenon lamp, flashes a beam of light with all the colors of the spectrum. That light then passes straight through our tiny liquid sample. And finally, a detector on the other side measures exactly how much light made it through. By comparing what went in to what came out, it knows exactly what was absorbed.
And check this out. This is how it solves for B, the path length. This is just a brilliant piece of engineering. The machine actually uses the surface tension of the liquid itself to form a perfect little column between 2 points. It's incredible. This creates a known precise distance for the light to travel through every single time. So clever.
So after the detector does its thing, the machine spits out a graph that looks just like this. This is the absorbance spectrum. What you're looking at is A from our equation plotted across all the different wavelengths of light. And you can see that different molecules absorb light differently. They create a unique signature. For DNA, that signature peak is right there at 260 nanometers. The height of that peak, that's our A value, and it tells us the concentration. It's that direct.
Now, measuring DNA is obviously a huge deal, but this law is far from a one-trick pony. It's a foundational tool that's used all over the place, in tons of different fields of science.
And you can really see that versatility right here. On the left, you've got that classic DNA peak. It's like a single snapshot in time. But on the right, you're looking at data from a kinetics experiment. The machine is taking measurements over and over again to track how a chemical reaction is changing in real time. It's the exact same principle, just applied in 2 totally different but equally powerful ways.
I mean, the list of applications is just huge. Every day, scientists are using it to quantify proteins, to see how thick a bacterial culture is getting, to analyze samples tagged with fluorescent dyes. It's even used for quality control in the food you eat and to monitor pollutants in our air.
So let's just zoom out for a minute.
Why does a principle that was figured out centuries ago for optics still matter so much? Well, because its impact stretches way beyond the research lab.
Inside the lab, it is the absolute backbone of modern molecular biology. It makes research in genetics, disease, and new medicines possible. But that same core idea, figuring something out about how it weakens a beam of energy, is at work in things like medical CT scans and in the systems we use to sense the health of our planet's atmosphere.
So, what's the big takeaway here? The Beer-Lambert law is this simple, elegant, and super reliable way to measure something you can't see, just by shining a light through it. At its heart, this powerful principle is all about doing one thing: turning an invisible property of our world into a visible, understandable number.
It really is a profound idea, isn't it? That light itself can be our tool to quantify the hidden world all around us. Which kind of leaves us with one final question. What will we learn to see next?